So it gets pretty repetitive, doesn't it? We have an experiment, we try to figure out the best way to analyze it. Once we figure it out, when it's an inferential statistic, we kind of do the same thing. When it was a two-sample independent t-test, we developed a t-obtained, figured out the t-critical, compared them. When our k was greater than 2, well, then we had to use an ANOVA. But it was still basically the same thing. We determined our f obtained, determined our f critical, and we compared them. What we're doing is we're expanding the toolkit so that we know how to analyze different types of experiments. And that's what we're doing today. We're adding a tool to the kit. These are experiments that are dependent samples. We've talked about independent samples t-tests, independent one-way ANOVA. These are dependent samples tests. Well, what does that mean? It's kind of the point. So I'll be talking a little bit about that and talking a little bit about how to analyze those. And when we get down to it, though, it'll be basically the same. Determine an obtained value, determine a critical value, compare them. But let's talk about those dependent sample experiments. There are two, really. Let's talk about those. So there are really, when you get down to it, two types of experiments. It says research designs. I should have probably said experimental designs. But that's a little bit misleading, to be honest with you. It's like people say there's two types of people in the world, cats and dogs. Wait, no, that's not what they say. Great start. There are two types of people in this world. People love cats and people love dogs. Well, we can divide people up in lots of different ways. We can divide experiments up in lots of different ways. But one of the common ways we talk about them is making a distinction between the types of groups we are studying. Up to this point, we've been studying independent groups. The idea is that we develop equal groups through random assignment. We take a sample, divide it in half, if we have two levels, and use random assignment to keep them equal. We then separately expose each group to a different level of the independent variable. Dependent groups are different. In fact, participants in a dependence group experiment are somehow related. They're not separate. They're not orthogonal, to use the fancy statistical word. How does that work? Well, in some way, each member of group 1 is paired with someone in group 2. There's a couple different ways you can do it. We'll talk about those ways. But instead of being independent from each other, they're actually related to each other. You'll sometimes hear dependent groups called related groups designs. The idea behind it is actually pretty sensible. The idea is if we have these related groups, we can help to minimize error, to minimize within subject variance. I'll talk more about that soon. Let's talk about the two basic types of dependent designs. The first type is the matched pairs design. Matched pairs. You ever heard of people who have arranged marriages? Sounds crazy to us, but in a lot of cultures it's not all that crazy. Could be pretty helpful, really. Well, someone decides that these two people should be paired. Well, we're talking about the same thing here, but of course we're not talking about marriage. We're talking about pairing two different participants in the experiment across the levels of the IV. The idea is that we take some variable that's really important and we hold it equal by taking two people that have the same score on that characteristic. So maybe, looking at our picture here, we have two 25-year-olds, one in group 1, one in group 2, and they're paired. They're a match. And then we have two 35-year-olds, and they're paired across groups, so on and so forth, so that we have that characteristic matched across groups, and then we split those pairs, so there's one in each level of the IV. And it holds that important characteristic constant. If age is important, make sure age is equal across groups, not based on random assignment, but based on matching them. There's one 35-year-old on each side. There's one 24-year-old on each side. There's one 19-year-old on each side. And you could do it with any characteristic. If you decide for the experiment that you're doing that religion matters, then you could have a Catholic paired with a Catholic on the other side. And you could have a Muslim paired with a Muslim on the other side, and a Jewish person paired with a Jewish person on the other side. So that you have each one of those persons on each side matched as a pair. And basically what you're doing is you're holding it constant. That characteristic is the same across groups because you've matched it and you've paired it. And that eliminates any variance, any error variance due to that characteristic. Basically what you're doing is you're taking a variable you think is important, that you think might be a confound, and you're holding it constant by making matched pairs across those levels of the IV. So if your groups differ at the end, it's not because of religion, it's not because of age, because you've matched them on that. Those things can't have caused the difference in the DV. As a result, it helps minimize error variance. So this is one way you can have a related sample. They're related because we've matched them on this characteristic. They're not independent of each other. In fact, they're dependent because you've made sure that you have a match across the groups. A couple of things to think about when you're considering the use of a matched pairs design, and this comes right out of your textbook, figure 11.2, but I just want to walk through this a little bit. The first is, are there one or two participant variables that might confound your results? They say one or two because you can't match them on everything, right? Look, I'm a 47-year-old, 5'8", 182-pound, former Catholic from upstate New York with a PhD in behavioral neuroscience and a size 10 shoe. You're not going to be able to match me, easily at least, on all of those variables in an experiment. But you don't have to, because they probably don't matter. You only have to match people on the ones that do, or at least the ones you think that do. So you can match people on age, you can match people on education level. You might be able to do both of those. You get to 3 or 4 or 5, well, then you better use random assignment and hope it works. Can you find an appropriate matching variable? Well, there's always something, right? Do you have a variable that theoretically is important? If you do, consider matching it. Does the matching variable sensitize the participants to the purpose of your study? Sensitization is one of the things you have to worry about in a matched pairs design. And the idea is that somehow this matching them on this variable is going to alter the effect of the experiment, aside from the IV. Here's a real one. Here's one that's not theoretical. Here's one that's practical. Can you do it? Can you find people to match on these characteristics? I remember a study that I'm quite fond of matched people on spinal cord injury. That's a weird one, right? People who have severed spinal cords, luckily, is a fairly small population. And they wanted to match across groups based on where that spinal severing happened. Was it thoracic? Was it T3 or T1? Cervical 1 or cervical 3, C1 or C3. So they had to match on that characteristic. And that's a really hard thing to do. They did their best. Wasn't perfect. And just how hard is it to do? Can you get it done? Is it possible? So these are some things to think about. I'll tell you, to be honest with you, for the most part, if you can have a big enough sample, I'm always going to tell you, you're better off on random assignment because it'll have all of those things equal across groups. But if there is one giant flashing light of a variable that you know matters a ton, well then, maybe matching it's okay. Look, we just have had an election, and political party is one of those things that's a big flashing light. And if you're going to do an experiment that's about, political decision making, then to leave political party to random assignment, unless it's really big groups, is probably a mistake. It's just such an important variable that you just have to match it. So you find, a Democrat to match with a Republican. so that you can have a pair for comparison. I wanted to show you another example of a matched pair design. In this example, researchers are studying a new diet. And one of the things that's very clear in studies of weight loss and nutrition and lifestyle and behavior changes is that the rate of weight loss is often greatly affected by the starting weight. As someone who's dealt with a food problem his whole life, it's very true. You start eating healthy and you lose weight quickly when you're at your peak. It's a little bit of regression towards the mean. But once you get too close to a healthy weight, it gets harder and harder, right? So one of the things that often happens in a well-designed study of a new diet is they match across the conditions for weight, starting weight. So we have here two groups, one on a new diet, one on an old diet. And you can see we've paired participants. So here we have two folks, one in each group that weigh 185, and all the way down to, we have one in each group that's 240. And now, they're exposed to either the new diet or the old diet, and we see if there was weight loss. By holding the weight constant, it allows for the control of a really big confounding variable. Could you have randomly assigned it? For sure. But to rely on random assignment with such a small group, I'm trying to count here, 2, 4, 6, 8, was that 9 participants per group? Bad news, because you need large groups to let that random assignment work. So in a position like that, matched pairs is definitely the way to go. So we saw the matched pairs. To be honest with you, though, the more common way in which a dependent measures experiment happens is called a repeated measures design. And basically what happens here is the participants serve as their own control group, and they're exposed to each level of the IV. I stole this picture from the internet, although I don't think I like it that much. But it shows you that we have A, B, C, D, and E. Those are your participants. And they are exposed to level 1 of the IV at time point 1 and measured on the DV. And then at time point 2, exposed to the other level of the IV and measured on DV again. And then you can compare the DVs. I made a different version of this, which I think is clearer. So we've got this young lady on her way to work, and she's one of our participants. We're going to expose her to IV level 1. So we've some variable we're manipulating, she's exposed to it. And then we measure the DV, M1. Then some time passes, and we expose her to level 2, and we get M2. We can now compare the effect of IV level 1 versus IV level 2 by comparing M1 to M2. And I want you to understand, she's serving as her own control group here. So if IV level 1 were 0 milligrams of THC and IV level 2 was 250 milligrams of THC, we would simply compare M1 to M2, and that would tell us, or at least suggest to us, the effect of THC on our DV, whatever that may be. A couple of things to consider. One is, does your IV produce a permanent change in your participant? If it does, well, you can't do this, right? Because now you're going to be looking at the cumulative effect of IV level 1 and IV level 2. 2, are there several participant variables that are likely to be confounded with the effect of the DV? Those participant variables that we just talked about in the case of matching design, if there's a bunch of them, you probably should just do a matching design. If, gender matters and ethnicity matters and weight matters and hair color matters, then you probably shouldn't do a repeated measures design. You should probably do a matching design. Another thing to worry about is mortality, right? Because you have to have these people come into your experiment twice. So we mean mortality here not literally as death, though it could be, but we mean people dropping out of the experiment. And if you've got 6 months or even 6 weeks between IV level 1 exposure and IV level 2 exposure, well, you might lose a lot of participants. Similarly, if it takes a really long time, you have to worry a little bit about maturation. Maybe a year has to pass or 2 years have to pass. And if you're doing an MRI study, the brain changes a lot in a year or two. So the differences might not be to the effect of your IV, but instead just maturation. And then finally, one of the things you have to worry about is the order effects. There's a bunch of things listed here. I'll show you what some of these things mean. But you really need to worry about the order effects. Because maybe being exposed to IV level 1 first and then IV level 2 second matters. And if you reverse the order, you'd get a different effect. So you have to be really worried about that. Your textbook takes some time to kind of define these things that are listed here. Carryover effect, practice effect, fatigue effect. These are very specific types of confounds that can result as a function of the repeated measures design. But they're very similar to other threats to internal validity that we've talked about in other contexts. Pretty simple stuff, y'all. So what about analyzing these designs? Well, it depends. And I mentioned this in my introduction. If your K, which is the levels of the IV, is 2, versus if your K is more than 2, 3, 4, 5, 6, whatever it may be, you're going to use one of 2 different designs. If your K is 2, you're going to use a dependent samples t-test. If your K is greater than 2, you're going to use a repeated measures ANOVA. Now, we're not going to talk any more about the repeated measures ANOVA, so let me just describe it briefly first. You get the exact same ANOVA table that you got in the independent samples one-way ANOVA. You're going to analyze the mean squares between divided by the mean squares within in exactly the same way. The calculation is different, but the idea is exactly the same way. If you have 3, 4, or 5 levels of your IV, and your groups are not independent, they're related, whether it be matching or repeated measures, you're going to use a repeated measures ANOVA. It's actually a little bit harder to do in SPSS, although, no, see, I shouldn't, this is what happens when you're old. I could tell you about the bad old days of SPSS. But in the olden days, repeated measures ANOVA were the absolute hardest thing to do. When you were coding, because it was a programming language originally, when you were coding to do an analysis, repeated measures ANOVA were an absolute nightmare. And when it first became a Windows software program in the mid-90s, early to mid-90s, it still didn't work very well. It works well now, but it's a little bit hard to do, like the actual mechanics of it, but I'll show you. Let's not worry about that now. Let's talk more about the dependent samples t-test. Very similar to what we've seen previously. We're going to calculate a t obtained. We're going to determine a t critical. All that's still the same. There is one little difference, and that's that it's all based on difference scores. An accidental pun there. Because we're going to look at the way the scores change between group 1 and group 2. Or in the case of repeated measure ANOVA, repeated measures design between the first exposure and the second exposure, or first measurement and second measurement. So there's a difference calculation. Remember, difference is our fancy word for subtraction, but you knew that. Let's look at the formula. Very simple formula. I've actually altered it so it looks a little bit funky here to make it simpler for you. There's some parts that are often included here that don't matter, so I've eliminated them, but it makes it look a little funky here. But it's T obtained equals the average D divided by what's called the standard error of the mean difference. We've talked about standard error of the difference before, or standard error of the mean before. This is the standard error of the mean difference. The D, the big capital D, stands for difference. We'll see that in a second here. So we have to somehow figure out the average difference and the standard error of the mean difference. The standard error of the mean difference is calculated this way. Standard error of the mean difference equals the square root of the variance of the difference divided by n. How do we calculate the variance of the difference? Like this. The variance of the difference equals sigma d squared minus sigma d quantity squared over n, all over n minus 1. That looks really familiar, right? Except instead of x, it's just difference. I'll show you how that works here in a second. So this is very similar to what we've done in the past. We're going to work our way up to the formula. So we're going to start here, calculate the variance of the difference. Then we're going to calculate the average standard error of the difference. And then we're going to calculate our t obtained. Okay? Let me walk you through an example here just in the PowerPoint, and then we'll do more of this next time. But this is a study of two therapies, rather a therapy for phobia. And we have 5 participants, Foofy, Biff, Cleo, Attila, and Slug. Sorry for their names. I took this from an old textbook. And we're going to measure their fear of spiders before therapy and measure their fear of spiders after therapy. Okay? Now, I hope you can see this is a repeated measures design because we're measuring Foofy twice, Biff twice, Cleo twice, etc. We're measuring them before the therapy, like they're their control group, and then we measure the effect of the therapy after they've done it. So Foofy gets measured twice, Slug gets measured twice, etc. So here's that again. And we can see starting at our first formula, which is our last formula, depending on how you're thinking about this. This is the formula for the variance of the difference. And we have the before therapy and the after therapy. And I want you to notice that those lines, they look like dashes. They're subtraction. We're going to calculate the difference between the first and second measurement for each of them. So 11 minus 8, 16 minus 11, 20 minus 15, and that's our difference scores. Plus 3, plus 5, plus 5, plus 6, minus 1. And what we're going to do is we're going to sum that difference. So plus 3, we get 3 plus 5 plus 5 plus 6 minus 1 is 18. And then we're going to calculate the average. 18 divided by 1, 2, 3, 4, 5 is 3.6. We're then going to make a d squared column, just like we would have done with x, but now it's d squared, where we square each difference. 3 squared, 5 squared, 5 squared, 6 squared, and negative 1 squared. We get rid of that negative there. And then we're going to sum that, sigma d squared. 9 plus 25 plus 25 plus 36 plus 1 equals 96. So we already have everything we need. Look at our formula. We need sigma d squared, that's 96. We need sigma d quantity squared. Well, sigma d is 18, so 18 squared. Divided by our n. One thing, and you might hear my children crying in the background, and I'm sorry for that. But one thing I should mention here is that n, when we're talking about repeated measures or matched pair design, the n represents the pairs of scores. So our n here is 5. So sigma d squared minus sigma d quantity squared divided by n all over n minus 1. Here's the math. You plug it in, and you end up with a variance score of the difference of 7.80. Okay? That's step 1. So we'll do the next part, he says. Smoothly. My apologies. A little technical problem there. So we've calculated the variance of the difference. So now we're going to take that and we're going to calculate the standard error of the mean difference. Standard error of the mean difference is simply that variance score divided by n, and we take the square root of that. So we take that variance score, which we figured out to be 7.80. We plug that in, and that's 7.80 divided by 5, take the square root, and that gives us 1.249 for our standard error of the mean difference. So we take that number, and we're going to plug it into our final formula. T obtained equals the average difference divided by the standard error of the difference. We figured out that standard error of the difference was 1.249. The average difference we figured out was 3.6. So we got 3.6 divided by 1.249 gives us a T obtained of positive 2.88. Cool. It's actually one of the easier calculations, right? Remember way back when I said, once you understand how to calculate variance and standard deviation, everything else will be easy? Do you see how I wasn't kidding? Everything is just a variance score because all of these inferential statistics are analyzing variance. This is the variance of the difference. And we now have a T obtained of plus 0.288. We do that with that what we always do. We go to our T critical tables, Degrees of freedom is n minus 1. I told you that, where n equals the pairs of scores. So for this example, it's 5 pairs. And we're going to do 2 tail 0.05, which gives us a critical value of 2.571, plus or minus, because it's 2 tail. We're simply going to place that on the distribution of the null and see how it looks. Here's our distribution of the null. We're going to put our negative 2.571, our positive 2.571, and then on top of that, place our t obtained, a positive 2.88. 2.88 falls in our region of rejection, which means we are going to reject the null hypothesis. And in doing so, we find that our therapy had an effect on our DV. We then report it just as we always do. T degrees of freedom equals 9 equals T obtained 2.88 comma P less than our alpha 0.05. If it had not been statistically significant, we'd reverse that and say P greater than 0.05. It really is that simple. So what we'll do next week, get some practice in these calculations, see how to do it in SPSS, and also see how to do repeated measures ANOVA in SPSS. Well, there you have it. Yeah, not all that complicated. We've got 2 different types of related samples experiments. One in which we match individual participants across the groups on some variable we think is important. And one in which we take an individual and we just follow them across all the levels of the IV, letting them act as their own control. Cool. There are advantages and disadvantages of each, as we said. Now the analysis, well, it's pretty straightforward too. If you have 2 levels of the IV, it's a t-test, except now it's a related samples t-test or a dependent samples t-test. We walk through that calculation, it's no big deal. Pretty simple, really. And then if it's more than 2, well, now you have an ANOVA, but we call it a repeated measures ANOVA. We didn't go through that calculation at all, and in fact we won't. We're only doing repeated measures ANOVAs by hand. By SPSS, my apologies. I said the opposite of what I wanted to, as I do. So we'll get some practice on calculating dependent samples t-test next week. We'll see how to do that same dependent samples t-test in ANOVA. It's actually a little bit complicated. And we'll do the same for repeated measures ANOVA. Okay. We're adding tools to our kit, but it's getting easier, isn't it? Same thing. Obtained, critical, compare, report. Bob's your uncle. Let's go.